we've gone through the three different approaches for searching: the centralized, the fully distributed Gnutella, and the one in between, the fast-track super-peer architecture. Here's a fourth approach, which is different from all of them. Once we go through, importantly, so the general algorithms used are called distributed hash tables. They make use of hash algorithms. The characteristics we'll see is that it's a structured peer-to-peer system. What that means, remember, is that there is information about the index, where to find the resources, stored on other nodes. Gnutella was an unstructured system where your nodes just store information about their local resources, do not store information about other resources. This is a structured system in that nodes will store index information about other resources, but it's a flat architecture in that there's no special nodes in the system. Distributed hash tables are a concept or a peer-to-peer algorithms. There are different implementations of them. So there are different protocols that implement and use DHTs. We're going to go through Chord, which is one of them. There are others. These are some older ones, and there are some newer ones. BitTorrent now makes use of distributed hash tables to find other peers, to find the peers which have the resources we're looking for. We looked yesterday about BitTorrent from the perspective of how do we transfer the data, but how do we find the other peers? Well, that's one approach that BitTorrent uses. BitTorrent, you can use different approaches. One of them that uses is distributed hash tables. And other systems use distributed hash tables, content distribution networks, mirror networks. So we'll go through how Chord works, the very basics of it. Remember, what we're trying to do is find a node which has a particular resource, the searching process. That is, there are a set of nodes, a set of peers. They have different sets of resources. If I'm looking for a resource, some resource R, in fact, I must know the key for that resource, so I search for a resource with some key K. In Chord, as an example distributed hash table algorithm, we have a set of nodes in the network, n nodes, and the aim is to distribute the files, the resources, amongst those nodes. And then make it easy to locate those files or resources. That's the aim. And to do that, we make use of hashing, a hash algorithm. We've mentioned before, a hash algorithm takes as an input some piece of data, variable size data, produces as output a practically unique small hash value. Small in terms of, for example, we'll use 160 bits. So a 20-byte value, think of it as a fingerprint that identifies the data. Two pieces of data will have different hash values. The same piece of data will have the same hash value, and the hash value is small. We'll use a hash algorithm. In this Chord, we'll use the SHA-1. It's just the name of a hash algorithm. There are others. MD5 is another one. We'll use SHA-1. We'll take the hash of an address of a node, of a peer, so the IP address, and in practice not just the IP address but also the port number, because it's an application running on some port, and maybe even the application identifier, another ID. But take the hash of the address of the node, produces some ID, some 160-bit value, and the hash of the file. Here it says file name, but in more general the file contents itself. So I have a 1 megabyte file I want to share on the peer-to-peer system. I take the hash of that file and it produces some key. So the file is the resource, we take the hash of the file and we get the key K. So nodes have some ID, resources have some key. Both of the same length, 160-bit values, in the same space. To explain how the search works, because for the search, if I'm looking for some resource with some key K, I want to find the node that has that resource so I can download it from them. Then conceptually we'll visualize the nodes as some circle. We'll see shortly some examples, but node 1, node 2, node 3, node 4, and come back around to node 1 again. So we'll visualize as some ring or some circle. Ordered by ID. You can go through. What I mean is this. Here is an example with 16 nodes. Starting from node 0, so the ID of this node is 0, node 1, node 2, and around to node 15. So a simple example, if we have 16 nodes in our peer-to-peer system, using Chord, those nodes have IDs from 0 up to 15, and visually we can think of them placed in a circle. Of course they're not, these are just 16 computers on the internet somewhere. But if your computer with ID 0, you'll have some special relationship with computer with ID 1. Even if it's on the other side of the world, we conceptually think about them located in a circle, in a ring. So a resource which has key K is stored at the node with the same ID. So I have some file. I take the hash of that file, the contents of the file, and the hash produces some small value. In the example that we'll go through, we'll use a smaller hash value. In real Chord, we produce a 160-bit value. In the example I'm going to go through, let's say we produce a 4-bit value. We use a 4-bit hash algorithm. Just to keep it manageable in the example. So if we have some file, if we take a hash of that file, we get a 4-bit output. Let's say in binary 0011, or in decimal 3. So the hash of the file gives us the value 3. That means we need to store that file on node with ID 3. So the file, the resource with key K, this is the key. So the key for this file is 3. That file needs to be stored on node 3. So if my computer has a file that it wants to make available in the peer-to-peer network using Chord, I have the file, I calculate the hash of that file, it becomes 3. Then I transfer that file to node 3, some other node in the network. So my computer, even though it makes it available, it is going to be transferred to someone else, potentially some other node. Why do we do that? To make search easier. So when I want to publish data in the network, I find the key value for that data and then transfer that data to some other node. The other node is the node with ID equal to 3. And as you guess, if someone is searching for node with resource with key equal to 3, then search should be easy because they go directly to node 3. So the idea here is to make search easier, and we'll see how that works. With a 4-bit hash algorithm, we have 16 possible key values. That is, we could have 16 unique files. With a 160-bit hash algorithm, we have 2 to the power of 160 possible files, which is many. So in practice, we have a larger value, but in the small example, we'll just use 4. The key space, the set of possible keys we can use, and the ID space, the set of possible IDs we can use, must be the same. 160-bit in real chord. In my example, if I'm using a 4-bit hash algorithm, I have 16 possible keys and 16 possible IDs. 0 through to 15 with a 4-bit value. And that's why you see in the later slides this circle with 16 nodes, 0 through to 15. So if we're using a 4-bit hash algorithm, in our peer-to-peer system, we can only have 16 nodes. Our network can only have 16 nodes, no more. If we're using a 160-bit value, the network can have no more than 102 to the power of 160 nodes, which is a large number, which is not a problem in the internet. That's the maximum number of nodes we can have in our network, but we may not have that many nodes. I can have 16 possible IDs, so I can only have 16 possible unique nodes in my peer-to-peer system. I may not have 16, I may have just 10 nodes at some point in time. 10 nodes in the system. If a node with some ID which is equal to k in our example, k equals 3, ID equals 3. If there's no node that has that ID in our network, then the resource is stored at the next node in the ring, the node with the next highest ID. So we'll come to the example shortly. Explain these concepts via the example will be easier. We'll demonstrate the concept that if a node joins the network, so we start with one node, another node joins, and new nodes join our network, then we need to reassign keys, and similarly if a node leaves the network. Let's get to the example as quick as possible. We'll demonstrate to insert data, to publish data in the peer-to-peer network. I have the data, the file. I calculate the hash of the data, like I did here. I've got the file. I calculate the hash. I get the key value. And then I find the node that stores or manages that key. Key value 3 should be managed by node with ID 3. Then I transfer the data to that node. And the data is stored on node 3. That's how I insert data into the system. And to search for a resource, I must know the key of that resource. So if I know the key of a resource and I want to find that resource, we do not calculate the hash of the data. That is, we do not have the data yet. We need to know the key in advance. We find the node that stores that key, which should be the node that has the data. How do we download the data? We can use any method that we like. HTTP, or as we saw yesterday, we could use BitTorrent protocol to exchange and download the data. That's not part of Chord. Let's see how it works through our example, and we'll come back to these slides when needed. So, we're going to use an example which uses a 4-bit hash algorithm. It's not realistic because if we have a 4-bit hash algorithm, we are only limited to 16 nodes and 16 possible files. In real life, there'd be many more. In the real Chord, there is a 160-bit hash value. But with a 4-bit hash algorithm, there are 2 to the power of 4 possible hash values, and therefore 2 to the power of 4 or 16 possible keys and 16 possible IDs. A maximum of 16 nodes are allowed in our network, and a maximum of 16 possible files can be shared in this network, no more. Because every file needs a unique ID or a unique hash value. And every node needs a unique ID, a unique hash value. So we have 16 possible nodes. So this just illustrates that node 0 through to 15. The hash values 0 through to 15. Let's put some nodes in the network to start this example. I've got, in this case, 7 computers on the internet. They want to be part of this peer-to-peer system. In this example, I've taken the IP addresses of those computers and hashed those IP addresses. It could be not just the IP address, it could be a hash of the IP address and the port number, or a hash of the IP address, the port number, and some other identifier. In this example, just the hash of the IP address. So an IP address is just a 32-bit value. I take the hash of that, applying my hash algorithm, and as an output, I get a 4-bit value, a 4-bit hash value. What is the hash algorithm used? Well, and how does it produce the value? Well, that's details that we don't care about here. SHA-1 is one hash algorithm. Our 4-bit hash algorithm, I've randomly chosen outputs. That is the computer with this IP address, 212.58.224.131. If we take the hash using our 4-bit hash algorithm, we get the output 0. Some other computer, we get 14, 3, 11, 7, 1, and 6. Okay? That's just for this example. So conceptually, we have 7 nodes in our peer-to-peer system that can be viewed as a ring. Node 0, because the hash of this IP gives ID 0. Node 1, 3, 6, 7, 11, and 14. So the black circles, the filled in circles, are the nodes in our peer-to-peer system. There is only 7 out of a maximum of 16 at this point in time in the peer-to-peer system. If a new node joins, then we'll take its IP address, hash its IP address, and obtain some value. And it should be, because in practice, if you use a large hash value, 4 bits is not large, but 160-bit hash value is large. If we take the hash of some value, we'd get a unique hash value as an output. That is, we'd get one of the other IDs. The idea is that each node, a node with ID 7, will store the resource with key 7. The node with ID 3 will store the resource with key 3. That's the idea. So that when we search, we can easily find the resource. Because if we're searching for a key 3, go to node with ID 3. So that node with ID 11 will store resource with key 11. Peer 7 will store key resource with key 7. Peer 6, key 6, 3, 1, 0, and 14. So that's the initial step. Every node manages the resource with the key that equals its ID. But there may be resources with key of 8, 9, 10, where we don't have nodes. So the rule is that the next node along manages that resource. So what we show here in the rectangles is the set of keys that are managed by a particular node. Node 6 manages key 6, as well as the preceding nodes which don't exist, 4 and 5 in this example. Node 7 stores the resource with key 7. Node 11 stores the resource with key 11. But since nodes 8, 9 and 10 do not exist in this peer-to-peer network, then node 11 also needs to store the resources with keys 8, 9 and 10. So we get what we have in this slide, the set of keys, I'd say, managed by a particular node. Nodes store key values from predecessor nodes to their own node, predecessors that don't exist. Before we search for data, let's insert a node. What happens if a new node joins a network? If the IP address of, so a new node wants to join this peer-to-peer system. Currently we have 7 nodes, 7 peers. A new node wants to join, it has IP address 72.103.16.4. We apply our 4-bit hash algorithm. We take the hash of that value. And let's say it returns the value 13. What changes here? We now have a new node. The hash of the node address is 13. Therefore, the identity of that node, the ID of this new node is 13. Where is it? Well, here. We need to, the new node becomes node 13. What happens to the keys? So we now have a black circle at position 13. What do we do with the keys? 14, the keys for 14 need to be changed. 14 currently manages the keys 14, its own, as well as 12 and 13, because nodes 12 and 13 do not exist. But if node 13 joins the network, then we need to modify the keys that node 14 manages. So that 14 would manage key 14, node 13 here would manage keys 13 and 12. So as a new node joins the network, we need to update the keys managed by the successor node. That is, for 13, the successor node is 14, the next node around. So every node that joins the network, we need to, potentially one other node needs to have its keys updated. Now imagine this is not just 16 nodes, but millions of nodes. It's a large network. The advantage here is if one node joins the network, there's just one other node that needs to perform an update, the successor node. If this was a circle of 1 million nodes, node 13 joins the network. It's only node 14 that needs to update the set of keys it manages. The other approximately 1 million nodes don't need to do anything. That is, joining a network is a simple step. It needs a small update, but very, very minor relative to the number of nodes. If there are 1 billion nodes in here, again, a new node joins the network, only one node needs to perform an update the key space that they manage. So the advantage of this scheme is that as a node joins the network, we do not need to modify much of the network. Only one node needs to be modified. Similar when we leave a network. This slide shows what happens if another node, not our node here, but node with IP address 130.220.79.115 with hash value 9 joins the network. 9 joins the network, then we'd need to rearrange the keys for node 11, the successor node for 9. Keys 8 and 9 are no longer managed by 11, they are now managed by 9. So that's the process of joining a network. Remember, in summary, the circles which are filled in are the nodes in the network. The rectangles show the set of keys managed by that node. A node managed its own key plus the keys for the predecessor nodes that don't exist, the ones before it that don't exist. We'll see the advantage of that when we do the search. Similar when a node leaves the network. In this example, node 6 leaves the network. It's no longer part of the peer-to-peer system. When node 6 was in the network, it managed keys 6, 5 and 4 because nodes 4 and 5 didn't exist. 3 did. But 6 leaves the network, so now 7, which prior to 6 leaving the network managed key 7 only, now needs to manage keys 4, 5, 6 and 7 because 4, 5, 6 and 7, or 4, 5 and 6 are no longer in the network. So again, a node leaving the network, we need to update the keys for the successor node. If we have 1 million nodes in the network, a larger network, one node leaves, we only need to do some updates at just one other node, which is simple in managing the network. When we say update, in real life it means sending some packets to inform the other one that it's got more keys to manage. The less nodes we need to send packets to, the less overhead of updating. Joining and leaving. So now this is our resulting network. We have 7 nodes in our peer-to-peer system. We have a maximum of 16, but there are only 7 present at this point in time. Nodes with ID 0, 1, 3, 7, 9, 11 and 14. And remember, the resources are stored on nodes where the resource with key 7 is stored on node with ID 7. Resource with key 4 is stored on node with ID 4. But node with ID 4 doesn't exist, so it's stored on node 7. When we search, we want to be able to find the resources quickly. How do we search? Here's a simple approach to search. Here's an example where node 0 is searching for a resource with key 13. Somehow node 0 has found they want to download a file. They know the hash value of the file. So maybe if we're using BitTorrent, the hash value of the file is available in the .torrent file. Recall from yesterday, the .torrent file contains the hash value. So node 0 knows the hash value, that is the key. They know it's 13 in this example. They want to find the peer that has the resource with key 13. Which peer has it? We know. Which peer? Which peer should have it? Peer 13. That is, if peer 13 exists, then it should have the resource with key 13. That's the basic concept, that resource with key 13 should be on peer 13, if it exists. Let's see one example of how we can search. So we send a query to nodes. The issue with a search is that we still need to know the IP address of some nodes, because we need to send the packets. If we're going to send a query, we need to send it to the IP address and the port number. We don't send it to a node ID. We use the Internet Protocol to send. So with search, we maintain a routing table. And the size of the routing table is important, because the more nodes we have, if a larger routing table, it becomes harder to maintain. Let's see what we can do in this case. In this example, which is not how Chord works, but we'll go through it first, each node has a routing table. And in this case, the routing table stores a route That is the IP address of the next node in the network. So the routing table for node 0 would be node 1 has IP address, and I have to go back to find it. Node 1 has IP address 64.233. $187.99. Remember, to get the node ID, we took a hash of the IP address. Similar node, let's draw a couple more routing tables. So that's the routing table for node 0, just one entry, the ID and the IP address. Routing table for node 1. Node 1 stores a route to the next node in the network, which would be node 3, IP address 129.42.18.103. In this simple example, every node has a routing table with just one entry. The entry is to the next node in the ring, in the Chord network. So I'm coming back to where we are. Node 0 has a routing table which says the next node in the network, node 1, has IP address 64, so on. Node 1 has a routing table which says the next node, node 3, has IP address 129, so on. This is a different routing table than what an IP router uses. This is a Chord routing table. Same purpose, but different implementation. It's got a different structure. It tells us to reach node with ID 1, send to IP address 64, so on. Because in reality, we need to send to IP addresses to reach a particular node. We send our packets to IP addresses. And all the other nodes would have a routing table with just a single entry. Now, the benefit of having a routing table with a single entry is it's easy to update. If node 1 leaves the network, no longer in the network, then node 0 will need to update its routing table. It will need to change it to some other value. For example, it will find out that node 3 and give the IP address of node 3. And so will node 1 need to update its routing table. Oh, well, node 1's no longer in the network. So as nodes leave and join the network, we need to update the routing tables. And again, that involves some overhead. Sends some packets to learn about the IP address of other nodes. We want to minimize the number of entries in the routing table such that as nodes join and leave the network, the updates are contained, they're small. The more table entries, the higher the overhead of the updates. So having a single entry in the routing table is good from the perspective of if something changes in the network, I only need some small updates to update my routing table. We'll see why it's bad by looking at the search. So every node has just one entry in the routing table. So how do we search? Remember, node 0 is searching for resource with key 13. Node 0 knows about one other node in the network. It knows about node 1. So it sends its search query to node 1. Because in the routing table for node 0, we just have one other node. There may be, well, there are other nodes in the network, but node 0 only knows about node 1. Sends a search query to node 1. Node 1 receives the query. Node 1 looks in its routing table. Okay, here's a query. The key is 13. The destination is 13. How do I reach 13? Well, from node 1's perspective, send to node 3. Because node 1 only knows about node 3. To reach anyone, we send to the next, from our routing table, we send to the node which has the closest ID to the key we're searching for. We're searching for 13. There's only one entry, send to 3. 3 will send to its next node, 7, 9, 11. It'll come to 14, and node 14 has the resource with key 13. So we've found the data. This is a simple approach to routing. It's not the approach used. The problem with this approach is that we need to send a lot of queries. To reach the node which stores the resource with key 13, we need to send 1, 2, 3, 4, 5, 6 queries through the network. Basically send to the next node in your routing table, they send to the next node until we reach the node which manages key 13, which is node 14. This approach has the advantage of a small routing table, easy to update, manage, low overhead, but a disadvantage of the search takes a long time. This is a small network of 16 nodes. Imagine now there's 1 million nodes here. The search takes many queries to reach the destination. This is how Chord works. So the previous one is not how Chord works. It's just to illustrate one approach. How Chord actually works is like this. The routing tables have more than one entry. We're still searching for key 13, but let's draw some routing tables. The routing table for node 0 you maintain more than one entry, and the scheme is to maintain entries, for example, to nodes which are 1, 2, 4, 8 positions away. So we double the distance from our node. Node 0 maintains a route to the nodes which are 1, 2, 4 and 8 positions away. So 1 position away from node 0 is 1, 2 positions is 2, 4 and 8. But of course those nodes may not exist. So ideally, node 0 would maintain routes to nodes 1, 2, 4 and 8. We'll see how that helps with the search shortly. But if those nodes don't exist, then we maintain routes to the next one that does exist. So node 0 maintains routes to node 1. Node 1 does exist. Should maintain a route to node 2, but 2 doesn't exist. The next node along that does exist is 3. So in fact maintains a route to node 3. Should maintain a route to 4. 4 doesn't exist. The next one along is 7. And to 8 doesn't exist. The next one along is 9. So in fact, these are the nodes that node 0 maintains routes to. In the previous approach, it maintains a route just to the next one along. In Chord, it maintains routes to 4 other nodes, or up to 4 other nodes. And the way that we work out which other nodes is this approach that they should be 1, 2, 4, 8 positions away. But of course, if they don't exist, take the next node along. So you can ignore this column, the first column. It's just showing how I calculated the second column. And of course contains the IP address of those nodes. I will not draw them. So our basic routing table, the IP address to reach that node. Let's go back. Just going back to some of our descriptions. The node 0 routing table, or sometimes called a finger table, the name chord comes from having a chord and using your fingers to reach out to different locations. The routing or finger table, we in theory maintain to nodes 1, 2, 4 and 8 positions away from 0. The ones that exist are 1, 3, 7 and 9. And I'll just write up 1, 2, 4 and 8 again. If we're searching for a particular key, node 0 will send to one of these 4 values. And the way that it works out is each of those nodes is assumed to manage some key space, some interval of keys. The first node is assumed to maintain the key 1. The second node, which should be 2 positions away, should manage keys 2 and 3. Let's go to our initial network. From node 0's perspective, assuming nodes 1, 2, 4 and 8 exist, then if we want to search for key 1, the nearest node should be node 1, because node 1 should have key 1. If we want to search for key 2, the nearest node should be node 2. If we want to search for key 3, using our scheming chord, the nearest node that knows about node 3 should be node 2. So we say that the key space managed by this second node is 2 and 3. These are the columns. This is the next node or the node. And this, I'll write, this is the IP address. And this is the key space. We'll use the key space when we search. From node 0's perspective, the third node that it maintains a route to is node 4. What key space, when do we send a query to node 4? When will node 0 send a query to node 4? What key should it be searching for? Of course 4, because if all nodes exist, node 4 should maintain key 4. So 4. And the idea is that if we maintain the next node to be 8, if we're looking for key 5, the fastest way to get there would be to send to 4 and then 4 sends to 5. Because 4 should maintain a route to key 5, to node 5. So from the perspective of node 0, to reach node 5, of the 4 that we have as an option, 1, 2, 4 and 8, the closest should be 4. So the key space that node 4 maintains will include 5, 6 and 7. And similar for node 8 through to 15. So let's see how that works. Assuming all nodes are there, then node 0 is looking for key 13. If node 0 is looking for key 13, it should be on node 13. Node 0 has 4 routes to nodes 1, 2, 4 and 8. Which one's closest to 13? Which one's closest to 13 from node 0's perspective? Out of 1, 2, 4 and 8, which one is closest to node 13? You are node 0. You know about 4 other nodes, node 1, 2, 4 and 8. You're looking for node 13. Which one are you going to send to which is closest to node 13? assuming we go around, because remember that's what every other node does. If we send to node 8, so we've got 4 options: send to node 1, send to node 2, 4 or 8. If we send to 8, now think from the perspective of node 8. Node 8 has 4 routes to nodes 9, 10, 12 and 0. 1 position away, 2 positions away, 4 positions away and 8 positions away. We're searching for node 13. If we're at node 8, we'd send to node 12 because that's the closest to 13. Now from the routing table of node 12, it has routes to 1 position away, 2, 4 and 8. Send to node 13. So if you look at it in the order of the ring, then from the perspective of node 0, it has routes to 1, 2, 4 and 8. If we want to reach 13, the closest would be to send to 8. It is sent halfway across the network, and then from the 8's perspective it would send to 12, and then 12 would send to 13. Imagine this ring has not just 16 nodes but has 1 million nodes. Okay? We want to reduce the number of queries we send. Using this approach, instead of having 1, 2, 4, 8, we'll have 1, 2, 4, 8, 16, we'll have more routes. But the approach would be node 0, if we're searching for someone in this area of the ring, it would send to node 500,000, halfway across the network. And then that would be sent to node 750,000, and then eventually would cut down the space. It's the same as your search algorithms. One way to search, you're searching out of a space of 16, cut it in half. Node 13 is not in this half, it's not between 0 and 8, therefore send to 8 and let 8 search. So we've cut the search space in half. Why doesn't 8 send direct to 13? Good question. We've assumed that a node has just 4 entries in its routing table. It only knows 0 only knows about 1, 2, 4 and 8. 8 only knows about 9, 10, 12 and 0. How did I get those numbers? The nodes which are 1, 2, 4 and 8 positions away. 1 position away from node 8 is 9. 2 positions away from node 8 is 10. So in theory, the routing table for node 8 would be to 9, 10, 12 and 0. Because node 9 is 1 position away, node 10 is 2, 4 and 8. Why do we choose this scheme? It's an efficient trade-off between having few entries in the routing table, we want as few as possible, but making the search fast. In the previous approach, we just have 1 entry in the routing table. That's good. We don't have to update the routing table much, but it's bad for search. Search is slow. Here we have a trade-off. Try to keep the number of entries low, but make search fast. And using this approach is one way to do that. So we cannot send direct to 13 because we only have a route to 12, 0, 9 and 10. So the closest to 13 in the ring will be 12, the one before it. 12 would have a routing table which would include a route direct to 13, and then we'd reach it. Why did we get here? So in practice, a node has a routing table. We can think it has 3 important bits of information. The next node, how do we choose the next node? It's the node which is 1, 2, 4, 8 positions away, but it must exist. So going back to where we were for node 0. Node 0, 1, 2, 4 and 8 positions. If the node doesn't exist, take the next one along. 1 position away is 1. 2 positions away, node 2 doesn't exist, so take the next node 3. 4 positions away, next node will be 7, and then 8, the next node is 9. So in fact, these are the next nodes we store. The node must exist. We store the IP address of them so we can send a packet. And we think about the key space that each of those 4 nodes manage. That is, now if I'm searching for a key 13, I will send to node 9. It's in this key space. If I'm searching for key 2, send to node 3. If I'm searching for key 6, send to node 7. So that's one way to think about how it's used. Of course, every node does that such that we'll try to minimize the number of search queries. Let's draw the routing table for node 1. In the ideal case, which other node should it route to? Assuming all nodes exist, node 1 should route to nodes 2. So we'll just write here, 2. What else? 3. 1 plus 4. Okay. And 9. Now that's if the nodes exist. 1 position away, 2 positions away, 4 positions away, 8 positions away. Which ones exist? 2 does not. So in fact, the next node along is node 3. This is the next node. 3 exists. Well, we've already got 3. We don't maintain 2 routes. We've already got it in our table. 5 doesn't exist. Next node along is 7. 9 does exist. So the next node that node 1 maintains routes to are 3, 7 and 9. Only 3 in this case because we had 1 that was the same. So it may be less than the maximum of 4. We'd know the IP addresses for those 3 nodes and the key space for node 3. What key space would it manage from the perspective of node 1? This is an exam question. Fill in a table. Fill in the routing table for a particular node. What set of keys, so if we're searching for some key, why would we send to node 3? That is, we want to fill out this column. Looking at node 1, let's try all the keys. If we're searching for key 2, who do we send to? We would send to, in practice, 3. If we're searching for key 3, I'll draw 3 here. It's the same, but I'll draw it here. It's a bit easier. If we're searching for key 3, we should send to this node, which is node 3. If we're searching for key 4, node 1 is searching for key 4 or node 4, it should send to node 3 because that's the closest that's before node 4. Key 5, who do we send to? We're searching for key 5. Who is node 1 going to send to? 7. Good. The best way to think about this is to think about the ideal nodes. The nodes, if they existed, would be 2, 3, 5 and 9. Node 2, of course, manages its own key. node 3 its own key, and to reach the next node, node 4, we'd send to also node 3. And you see the pattern. If you look at this column, it's the key space is from that node up until but not including the next node. 2, okay, that's it. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0. Key 1, node 1 should have key 1. We don't need to worry about key 1. If we're searching for key 1 and I'm node 1, I should have it. So 9 to 0, 9 to 1, 9 to 0 in this case. So to calculate this key space, look at the ideal node. Let's look at this node. But in fact, we only have routes to these nodes, just 3 in this case. So in fact, we join these together to reach, find key 2, 3 or 4, send to node 3, 5, 6, 7, 8, send to node 7, and so on. 9 to 0, send to node 9. That is expressed, this diagram is showing the routes from node 0. This is the routes from node 1. There are only 3 in this case. And similar for all other nodes would have their routing table. Make some space. Let's search. Remember, that's our goal. Node 0 is searching for key 13. Then for the search, we just use our routing table. Node 0 searching for key 13, look in the key space column. Where does 13 fall? It falls within 8 to 15. Therefore, node 0 sends to node 9. This is the routing table for node 9. It has routes to 11, 14 and 1. So now the search, node 0 is looking for key 13 from its routing table, should send to node 9. Node 0 sends to node 9. Node 9 looks in its routing table. We'll go back. Here's the routing table for node 9. It has routes to 11, 14 and 1. And in its key space, you'll see, if you work out the routing table, that node 9 will send direct to 14. Because in the key space, it will tell it to send to 14. 14 has key 13. We've found the resource. Our search is complete. We're trying to trade off 2 different things. One, we want to make the search query fast, send as few messages as possible. 2, we want to make the routing table small, so that when nodes join and leave the network, updating the routing table takes little effort, doesn't require much overhead. The larger the routing table, the larger the update cost. The larger the routing table, the shorter the search, if we design it correctly. So this approach of taking routes to nodes 1, 2, 4, 8 positions away is this one way to implement this trade-off. We get a small routing table even if we have a large number of nodes, and our search is fast. In this example, just 2 queries. Using the routing table where we just have 1 entry, small routing table, but the search is much slower. We need to send many queries between the nodes. And that's where the advantage of Chord comes in. Reasonably fast search, reasonably low overhead of maintaining routes. Questions before we look at some other parts? We'll go back to the descriptive slides. Any questions?
Yes.
Now's the time to ask. You've got... routing table 1. So the key space column, think of it as we're going to use it with our search query. The way that we'll use it is if I have a query that is searching for some key, to find out which node to send to, I'll look in the key space column, and that will tell me the next node to send to. So to reach node managing key 13, which will be in this space, send to node 9. So it's in fact, maybe I've drawn it backwards from how we normally draw routing tables. To reach one of these nodes, send to this next node. If the destination is a node that manages a key in this space, send to this next node. So how do we calculate that? Assuming all nodes exist, because in advance a node doesn't know which nodes exist and which don't. So assuming all nodes exist, the best way, and back to our ideal network, where are we? If all nodes exist, this approach of maintaining routes to 1, 2, 4, 8 positions away from node 0, to reach anyone in this half of the network, from 9 to 15, send to node 8. That is, we have routes to nodes which are close to us, 1, 2, and 4. For nodes in the ring which are a long way away, if we go in one direction, 9 up to 15 are a long way away from 0, send to a node which is close to them, which is halfway across the ring. And then the idea is that that node should have routes to nodes which are close to it, which are on this half of the ring, which are 9, 10, and 12. So we cut down the search space. If we're searching for something over here, between 12 and 15, send to 8, so that we don't have to worry about this half. This one sends to maybe 12, because it doesn't have to worry about this quarter. And then this one cuts in half the search space all the time, and eventually we get there. Yep. In a large network with only a few users, it will work, but it may not give us many efficiencies. We still need to have routes to some of those users, but all right, if we had just node 0 and node 5, or node 0, 5, and 11, they would all have routes in their routing table, but it will work in that 0 will have a route to 5 at least. Each node at least has a route to one other node. If there are only a few nodes, then we don't have to send so far. If there are, let's imagine there are a lot of nodes. Draw a ring with 1 million nodes. I'm node 0, I'm searching for key 800,000 out of 1 million. Following this approach, it's key 800,000. I don't know which node exactly exists around there. Maybe it exists, maybe it's not. So node 0 sends halfway around the ring to node 500,000. And then the idea is that node 500,000, which will be down the bottom of the ring, would send to node 750,000. We're looking for 800,000. And then we'd cut the search space in half, and then node 750 would send close to it, which would be the number which is closest to 800,000 from the node around here's perspective. Mathematically, how long does that take? With a larger network, we have more entries in a routing table. In our network with 16 nodes, there's a 4-bit hash. We have 4 entries in the routing table. 1, 2, 4 and 8 positions away. If we have 1024 nodes, which is a 10-bit hash, how big is our routing table? Well, we have positions 1, 2, 4, 8, 16, 32, 64. That is, I have a route to a node which is 1 position away, 2 positions away, 64. I have 10 entries in my routing table. I'd have routes to nodes which are from 1 position away up to 512 positions away, halfway across the network. If you imagine there are 1,000 nodes here, node 0 would have a route to nodes which are 1, 2, 4, 8, which is close here, and the furthest would be node which is 512 positions away, which would be the other half. That is 10 entries. If we're searching, we'd send, if we're searching for something in this area, we'd send to here, that would send to here, and then they would be closer and closer. We get closer and closer. Large network, 1 million nodes. How many bits? Say 20 bit, 20 entries. Which is not so large, a routing table with just 20 entries, with 1 million nodes in the network. So a large peer-to-peer system. We only need to maintain a routing table which has a maximum of 20 entries, maybe less. Which is not so bad, because as nodes leave and join, yes, we need to potentially update that. That adds some overhead. But to search, what's the worst case time to search in that case? How many queries do I need to send? Let's look. Let's look at the worst case for our simple scenario. Node 0 is searching for node 15, or key 15. Node 0 will send to 8. 8 would send to 12, because 8 would have routes to 9, 10, 12 and 0. We're searching for 15. 0 sends to 8, 8 sends to 12. 12 has routes to 13, 14, 0 and 4. So 12 would send to 14 and 14 would send to 15. The worst case in this case, 0 is searching for 15, would take 1, 2, 3, 4 queries. The worst case with 16 nodes, 4 queries. The worst case with 1 million nodes, 20 packets are sent to query through the network, which is quite fast.
Why 1, 2, 4, 10, 16 like this?
Because that gives us this structure that if we're searching for someone over here, we can go halfway across the network. We don't need to search in this space. So the way to search is to work out which half the key is located in. Is it in 0 to 8 or 0 to 7 or 8 to 15? So we work out which half. Okay, it's in this half. So let's send to a query, the query to this node. And then from this space, we cut that in half. That is, okay, we're looking for 15. So it's not in this half, it's in this half, which is the quarter of the space. Send it to 12. And now this one cuts it in half. So by cutting in half is the optimal way to reduce the number of queries in that case. You've probably done that when you implement search in software. Yeah, search through in an array for some entry. Yeah.
If we have 20-bit networks and we have only insert 0 and the last 3.
If we have 1 million nodes in potential, so this is the maximum number of nodes, but the actual number of nodes, we just have what, 3? Is that what you're saying?
Yes.
Every node has up to 20 entries in their routing table, so most likely if we have 3 nodes, they'll just have entries to everyone. Search is immediate. Send a query to that node. So search is fast. So that's easy in that case. So if you have a small number of nodes, then it's still okay, because we do have multiple entries. So the gain is for a large network, many nodes, we need just a small routing table. 20 entries is not so bad, because we want to have a small routing table, because when a node leaves or joins, we need to update that routing table. We need to refresh it. That incurs some overhead. The smaller it is, the less overhead of updates. And we've designed the routing table in a way such that the number of queries we send is small. And the design keeps the routing table small and means we can do a fast query of this 1, 2, 4, 8 positions away. Any further questions on this? Yeah?
About the key space, how can we know the neighbor that we have to store in the routing table?
How do we know what you mean with this? Or
Yes, the key space column.
uh,
It has the key that ID is itself and its neighbor.
This is, in fact, we don't need to store this. This is just showing how the algorithm works in that, okay, these are my next nodes. Which one do I use when I'm searching for a particular key? Well, I use the one which either has that or should have that key. Should have key 2, should have key 3, 5 and 9. Or the one that's closest to the node that will have that key, but before it. So the one that is closest to node, if we're looking for key 4, the closest, because we don't maintain a route to node 4, only to 3 and 5, the closest to 4 that is before 4 is 3. So that's how we get this value. The closest to 7, or the closest to 8, but it is before it, is 5. Or in practice 7, node 7. So that's how we cut this search space in half each time. Send to the node which is closest but before, and then that one should have routes which are almost direct to the destination. How do you calculate this key space? If I ask you in a question, well, you just look at these values. Even if I don't ask you to calculate these values, the ideal nodes, you can. 1, 2, 4, 8 positions away, which nodes exist? And then looking at this first column, okay, the key space comes directly from 2 up until 3, but not including 3. 3 up until but not including 5. 5 up until but not including 9, and back to the start. Key 1, we don't need in the key space there. It's just a way to think about how the search would work. So we just saw how Chord does the search. This was the example that we went through at the start, which is not how Chord works. It was if we used a routing table of just one entry, which is good because we just need one entry per node. Have 1 million nodes, just need one entry. But search can be very slow. The worst case search is if we just have one entry a million nodes, the worst case number of queries, it was 1 million. Send to my neighbour, they send to their neighbour, and it goes all the way around across to all 1 million nodes. So that's bad. So that's why the chord approach is a good trade-off. Let's come back, just go back to the descriptive slides and see if there's something we've missed. So in Chord, every node has an ID, every resource has a key, and they use the same space. That is, we use a hash value of the address to give an ID, a hash value of a file, not a file name, a file to give a key, and they're using the same space of values, the same set of values. In Chord, it's a 160-bit value. We think of the nodes as some circle, ordered by their ID. Not all nodes exist. So the idea is that a resource with key K is stored at node with the same ID, but if that node doesn't exist, the resource is stored at the next node around in the ring. To join a network, there needs to be some reassignment of keys that are managed with the successor node, and same when you leave a network. If you have 1 million nodes in the network, one node leaves, then we need to update just one other node. The other 999,000 don't have to worry if one node leaves. So that's easy to update. I'm a node in the network. I have a file to share. To insert that data into the system, I calculate the hash of the file, find the key value, and then send the file to the node that manages that key value. If my key is 20, I will send it to node 20, or the next node, the node that needs to manage key 20 if 20 doesn't exist. So even though I have the file, it's stored on some other node, or I transfer it to some other node. You can adapt that so that you don't transfer the node, but you transfer some address. But the approach is that the resources are distributed amongst the nodes in the system. So that's inserting data. To search, as we've seen, we need to know the key. For example, connected with BitTorrent, the .torrent file contains the hash value of the file, the key. Once we know that, we use our approach of looking up the routing table. Not using simple routing, but using the chord routing, where a node maintains routes to nodes which are 2 to the I minus 1 positions away. This 1, 2, 4, 8 positions away, depending upon the size of the network. This is just some way to write down the routing table, what I've drawn up here. And you can think of it, or let's look at our table. In order to find a node that stores the resource with key 4, 5, 6 or 7, send to node 7. That's how we interpret our routing table. If you look in past exams, you'll see sometimes I give you an empty table with the columns and ask you to fill it in, and then ask you to do a search query and see who it's sent via. And that's just an example of the steps of the search query. The key benefits: a node stores information about a small number of other nodes. Remember, the benefit of Nutella, the fully distributed system, was that you only store information about your own node. It's a unstructured system. You don't store information about other nodes. The disadvantage of Napster is that the server stores information about all nodes, the entire index. Here we store information about a small number of nodes, meaning updates as things change is easier. We store routes to m nodes if there are 2 to the power of m nodes in the network. It reduces the maintenance between nodes. And The other benefit is that we can locate resources via queries quickly. We've gone through this example. The last slide summarises those 4 approaches, plus another one. Gnutella, Napster, so the 2 extremes of fully distributed versus using a server. The one in the middle, super peers or fast track, and then Chord. And this other one is full replication, means if you want to share files, just copy the file to every other node. That's the replication approach. And some approximate comparison in terms of the time to find a resource, the latency, search query, the number of messages needed, the cost of updating, and the amount of storage needed. You don't have to be able to work out the values, but let's just explain some of them. For example, for Gnutella, a directory server, the latency of a query is not dependent upon the number of nodes, because a query always goes to the server. So if you have one node in your system, you send one query to the server, get a response. If you have 1 million nodes in the system, with Napster, you send one query, get a response. So the latency or the time to get a response does not depend upon the number of nodes. It's fixed. So we say that that's 1 or 1 unit, for example. With Gnutella, the time to get a response depends upon the number of nodes. The more nodes, the longer it takes to get a response. And it's in the order of log n. So if we have 1 million nodes, if we log, say, base 10, it's in the order of 6. If you go up to 10 million nodes, it's slightly larger, 7. We're just using, say, the big O notation, or giving the approximate order. Let's look at another one that may be a little bit easier to understand. The number of messages that are sent. When we send using Gnutella, we send a lot of messages because we broadcast. This is N up here. The more nodes in the network, the more messages we send. So this is bad from the perspective of the unstructured approach. With Napster, we just send one message. No matter how many nodes in the network, we just send one query to the server. So that's good. As the number of nodes increase, the number of messages we send increases for Gnutella, or an unstructured approach. With super peers, it depends upon the number of super peers. Remember, we send to a super peer, and potentially that needs to send to other super peers. So if the number of super peers is relatively small, that's not so bad. But as that grows, as C, the number of super peers grows, then this number, the number of messages we send, gets higher. Yep. Full replication is, okay, everyone has some files. Before we start, I transfer my files to everyone. I make a copy on your computer and everyone's computer. So everyone has a copy of all my files. And now when I want to search, I've found the file. I have every file. Therefore, when I search, I don't need to send a query. I have a copy. The data is replicated across all other nodes. No, this is an extreme case. With a large network, of course, it will not be feasible. If we have 5 computers, maybe it's feasible. Just copy your files to everyone else, and then everyone has a file. It's just showing search and the number of messages we send is great. But to update, something changes, I need to send to every other node. If we have 1 million nodes, the update cost is too large to update. Just a comparison. So update cost is if something changes, what it takes to update, how much data we need to store. We see, so the green ones are good, red ones are bad, orange are not so bad, but log end is quite good because logarithm, as the number of nodes grows, the cost grows, but only by a small amount. So log n is okay as well, it's acceptable. For Gnutella, the number of messages we send is the problem. Broadcast is the problem. For Napster, all good. Storage, not so bad. But we have a centralized server, and it's not captured here. If that fails, the whole network fails. That's the problem with Napster. Full replication, fine for searching, no good for distributing the data. Super peers is better than Gnutella, but still, if our network grows, the number of super peers grows, and still our number of messages can grow. Distributed hash tables, and the example is Chord, is not bad for all of them. With a large network, these are small values. So that's why Chord is considered a good alternative to all of these, and it's used in practice in a number of large peer-to-peer systems. Because even though it's larger than here, increase the number of nodes to 1 million, 10 million, still this is a small value. That is, it increases the cost of, increases the time for queries, it increases the number of messages, but only by a very small amount. So a log n is not bad. So it's a good trade-off in all factors. That tries to just summarise and compare. You don't need to remember these or even calculate them, but just understand the trade-offs between those 4 different approaches. Gnutella and fully distributed, Napster and the centralised, Fast Track, which is a combination of the two, and Chord and distributed hash tables. And I think that summarises what we've talked about. We haven't talked about security, and we're not going to. So we're finished. Any questions on Chord in the last few minutes? We have a chance.
Which one do we use?
Different peer-to-peer systems have used each of them. As we said, Napster, Fast Track and Gnutella have been used in practice. Nowadays, for example, BitTorrent, in many cases makes use of distributed hash tables. I think it's an option. That is, it can use a centralised approach using the trackers, but it can also, if the option is turned on, to use distributed hash tables. So that's becoming more common, especially for larger systems. Just briefly, the exam from 2 years ago, although we don't have much time. Here's an example question from 2 years ago. Here's the Chord network. Answer some questions about it. Okay, it's just grown from 16 up to 32 in this case. But just to show you the types of questions, so it gives you some setup about which peers exist. We did it slightly different 2 years ago, but same approach. There are some peers in there or some hashes of file names or files, which nodes exist. So it gives you a set of keys, asks you where are they stored. You don't have this exam, this is 2 years ago. What is the maximum number of peers allowed in the network? And the answer is 32. Our Chord ring has 32 nodes. We have a 5-bit hash value. So the maximum allowed is 32 in this simple example. Because we have to have unique IDs. And if we only have 32 different values, we can only have 32 different nodes. Work out, given the key, work out which node maintains the index. We haven't called it an index here, but which node stores that key. So if the key was 7 and node 7 exists, then the indexer would be node 7. If node 7 didn't exist, then you need to know which node stores key 7. What happens if a node joins the network? So this moving of keys or rearranging of keys, and fill in the tables, which is this really. I give you the number of positions away as a reminder. Work out the neighbour, the next node, and the key space in this column. All right, it takes a bit of time, and I may not give you all of them, but then you can use it for searching. Given those tables, show me which nodes the search query sent via. Explain what's the advantage of using this 1, 2, 4, 8, 16 structure. Was there another question? Look, in last year's exam, or one of the other exams, and I think there was a question like, okay, what if we don't use this 1, 2, 4, 8? What if we use something like 1, 2, 4, 6, 8, 10, 12? That is every 2 positions away as the routing table. What's the advantage and disadvantage? What's the disadvantage?
Too large routing table.
Yeah, we will have more routing table entries. If every second node I maintain a route to, then out of 32 I'd maintain 16 routes. But with Chord I'd maintain only 5 routes. But the query may be faster. So the more entries generally, the more maintenance cost, but the faster the query. Any questions about Chord? There are questions in the past exams which are very similar to what we've gone through today. Worth practicing. Let's briefly then go through last year's exam. Last lecture, last 10 minutes, just have a quick look at last year's exam, a quick last sign of the attendance sheet. I haven't written the exam yet, and I won't until sometime next week, so I cannot give many hints. It should be similar to last year. It's just covering the topic since the midterm. Here's a question which asks you to explain the difference between different technologies for delivering IPTV in the service provider access network. So remember, in IPTV, we have the network that connects from your home to the core network. That's usually the bottleneck, the slowest part. So the advantages of using ADSL2+, fibre to the home, and fibre to the node. what technology to use in your home network, wireless LAN or Ethernet. Draw a diagram of that entire network. Here you can quickly calculate this one. We have a video session requires 5 megabits per second of core network bandwidth. The capacity of the network is planned to be 10 gigabits per second. So the core network can carry a maximum of 10 gigabits per second or 10,000 megabits per second. Each video requires 5 megabits per second. What is the maximum number of users or channels of standard definition TV that can be supported if multiple unicast is used as a delivery mechanism? Multiple unicast is just unicast. We send multiple copies. What's the answer? We have one video takes up 5 megabits per second. We have a capacity of 10,000. If we use multiple unicast to deliver from the TV station to the users, you either need to give me the maximum number of users or the maximum number of channels. Which one is it going to be in this question? Users or channels? Why users? Unicast, so one set of packets for each user. We're not using multicast, so we cannot, for every user watching some channel, we need to send one stream of packets. If there are 2 users watching a channel, the same channel at the same time, we still, because we're using unicast, we still need to send 2 separate video streams. So it's going to depend upon the number of users. If we have a capacity of 10,000, each user requires 5 megabits per second. 10,000 divided by 5 is 2,000. We can support 2,000 users at once. So that's simply the capacity divided by per user required. If each user is watching one channel, then we can support 2,000 users because each user consumes 5 megabits per second. We have a capacity of 10,000 megabits per second. Simple. But then, what if we use multicast? Watching TV, multicast, what can we support? Now with multicast, if we send one channel to 10 users, we just use one stream. With multicast, we just send a copy once. So in the best case, if there are 50 users all watching the same channel, I use up 5 megabits per second because I just send one stream using multicast. So now it's independent of the number of users. I can have 1 million users. I have 1 billion users in theory. So what limits us now is the number of channels. If I've got a capacity of 10,000, each channel consumes 5 megabits per second, each TV channel, then I can support 2,000 TV channels. (2,000 channels and an unlimited number of users per channel, in theory, because of the multicast approach here. Some other questions about, here's a slightly different one, some about IPTV. This one's about voice. The G726 codec produces a sample size of 20 bytes. So remember back to voice. We sample the voice, we sample at some rate, produce some sample size. and send those samples as packets. So this specific codec, G726, you don't need to know how it works, but it tells you every sample is 20 bytes. And it has a sample interval of 5 milliseconds. How many samples per second? How many? Louder? How many samples per second? How many samples per second? Sample interval is 5 milliseconds, means every 5 milliseconds I record a sample. So in 1 second I'd record how many samples? 200? 5 milliseconds? With a sample every 5 milliseconds, there would be 200 per second. Every sample takes up 20 bytes. But note the way that the protocol works, RTP takes the bytes of multiple samples and puts them into a packet every 20 milliseconds. So let's say we're sampling over time. These are the samples, 5 milliseconds. Every 20 milliseconds, your computer sends a packet. So how many bytes does a packet contain? Again? How many bytes does our RTP packet contain? So we sample every 5 milliseconds, but we generate a packet to send, so our computer samples, but then just sends a packet every 20 milliseconds. We don't send a packet per sample. In this case, we send 4 samples per packet. Per RTP packet. Every sample contains 20 bytes of data. So 4 samples contains 80 bytes of data. We're sending 80 bytes of data every 20 milliseconds. That means we're sending RTP packets every 20 milliseconds or 50 packets per second. $50 packets per second. A packet every 20 milliseconds gives us that, means a packet, 50 packets per second. Every packet contains 4 samples. Each sample is 20 bytes, so a packet contains 80 bytes of data, 50 packets per second. It's an RTP packet. You need to add on the header. At the end of the exam, it shows you the size of the headers. 4 samples per RTP packet means 80 bytes of payload of data, plus the header of 12 bytes of RTP, and that's at the end of the exam, 8 bytes of UDP, and 20 bytes of IP, plus 5 bytes of data link layer. I think that's in the question, which totals up to 125 bytes per packet need to be sent by your computer across the link. And sent every 20 milliseconds or 50 times per second means 50 times 125 is equivalent to 50 kilobits per second. So your computer is sampling voice at some rate, producing samples, putting them into packets and sending those packets. And the amount that is sent across the link works out to be 50 kilobits per second. And I think above the question says, how many calls can you support given some capacity? What's our capacity? Our capacity is 10 gigabits per second. So 20,000 calls. 20,000 times 50,000 is, was that our capacity? Is a million is 1 gigabit per second. I have to check the question. But the capacity divided by 50 kilobits per second in that case. So the challenge there was working out the packet size. And over the next week, you're going to go through the remainder questions and the questions from last year. So when's our exam? The last day of exam week, I think. Is it? The 12th? Okay, the last exam of the period. Between then, come and see me if you have any questions about any of these topics. I will send this time an email with the hints about the number of questions, but it'll be very similar to last year's exam once I write it.
Teacher, he said that don't give too much question.
No, of course not.
We cannot finish it.
Last year, how many questions? There's question 2. 4. See, only a few questions, but some are maybe quite long. There you go. Shortest exam I've ever created. 6 questions, not many. Okay, enough. We'll see you during the week. Answer any questions. I haven't looked at your assignments yet. I'll look over them over the next week and give you some feedback or some results. Otherwise, we're done. Well done. We made it through.